Hello students, today I will discuss about the acceleration transformation under Galilean transformation. So, in my previous lectures, I have talked about the velocity transformation and the length transformation. So, in my previous lecture, you must remember the velocity of any point particle who moves from P to P prime with respect to S prime frame U prime is U minus Vi. Here we have taken the simplest example of the relative velocity between the frames. That means S prime frame is moving with a relative velocity of V along x axis. So that's why here only x component comes. If the velocity of S prime if the velocity of S prime frame had three non-zero components, then simply the equation would transform to something like U prime is equal to U minus V, where V is equal to Vxi plus Vyj plus Vzk. Now to find out the acceleration, we simply have to differentiate equation 1 on both sides with respect to t. What we get? d dt of u is equal to d dt of u minus v. Now, since t is t prime, we can write on the left hand side in case of t d dt prime. So d dt of t prime u cap is equal to d dt of u minus d dt of v. Again, since v is uniform velocity means that does not change with time. So, dv must be 0. Uniform means constant. So, this quantity would be 0. So, this will be simply du dt. Now, the left hand is nothing but the acceleration of the particle with respect to S prime frame, and right hand side is acceleration of the particle with respect to S frame. So, this is our result. So, we can say that the acceleration is invariant under Galilean transformation. Now, previously we have seen that the time interval is invariant, time is invariant, length is invariant. So, till now we have length and time are invariant under Galilean transformation. So in classical mechanics, as we know, length and time are invariant. So this follows the assumptions of classical mechanics. Now another assumption taken in Galilean transformation. What is another assumption? That the mass is invariant under Galilean transformation. So this assumption one was taken, and also we know that these three fundamental quantities, that is length, time and mass, do not change in classical mechanics. And what we get in Galilean transformation? In Galilean transformation we also get that length, time and mass are invariant. That is, these quantities do not change with respect to the relative velocity of the observer. So these three are the important conclusions of the Galilean transformations. Now, since mass is invariant, so we can say that if from Newton's first law, if there is some acceleration, that means there is some force associated. There is some acceleration means there is some force associated. Now, as we get from equation 2, what we get? From equation 2, what we get? We get acceleration in S prime frame is equal to acceleration is S prime. Now, multiplying mass of the particle, which is m, on both sides, what we get? We get m into a prime is equal to m into a. Now, from Newton's second law, we know that what we know? Applied force is equal to mass into acceleration. So we can simply say that from this equation 3, we can put the applied force in S prime frame. S prime frame applied force S prime is equal to m A prime, and in S frame applied force F is equal to m A. So now we can say that A prime is equal to F. So this is our equation 4. So force is invariant under Galilean transformation. Also, in classical mechanics, we know that force does not change if we see the acting force from some moving frame or from rest. So, we can say that the nature and magnitude of applied force do not depend on the relative velocity of the observer where in inertial frames. Remember that all the calculations we are doing here with inertial frames, and frames means observer. Actually, frame S is at rest means observer. Here observer is at rest, and here observer is moving with uniform velocity. So what we get from Galilean transformation? That like Newtonian mechanics, in case of Galilean transformation also, the three fundamental quantities, that is length, time and mass, does not change. That is, these three quantities are invariant under Galilean transformation. That means whether you are at rest or you are moving, you will always measure same length, same time and same mass of a particle in case of inertial frames. So what we learned today? We learned that under Galilean transformation, acceleration of a particle is invariant, and under Galilean transformation, force applied is also invariant in case we are in inertial frames. That means both the observer at rest and the observer moving are in inertial frame of reference.